Now the more complicated one is the electric quadrupole term. And again, we have seen something similar in the electrostatic problem because even in electrostatic, we have considered the quadrupole term also. Now remember the quadrupole term is this one, J plus N dot J, and the x point direction, x point. All right. So to do that, to get to what we want later, we'll do again some vector identity manipulation. Okay, and to do that, we'll also involve integration by parts. So the first thing we'll do is to make it more complicated and then simplify it. Okay, the way to make it more complicated is just writing is like introduce a gradient operator. So instead of writing J, we write it as J dot gradient pine of x pine. So J dot into a kind of like a tensor. This is gradient pine of a vector. Okay, because we have seen this before. If you are taking a gradient of a vector, spatial vector, you actually get a so-called identity matrix. Okay, and identity matrix dot into a vector is the vector itself. So just J is just equals to this one. So we are kind of making things complicated. J go to this one. All right. So, but we'll then simplify it using some other vector identity, but we'll make it more complicated first. Now exactly the same thing happened here. So the second term is we'll write this bracket J dot N, we'll write J dot gradient pi N dot X pi. Okay, because gradient pi of this N dot X pi, this dot product between this vector and dot X pi, N doesn't depend on X pi, so gradient pi doesn't operate on N, only operate on X pi. We take the gradient pi of this vector, you get exactly this vector out. So this you get the N. So instead of writing N, you're writing it like this. And again, you make it more complicated. But after you're writing that, you can simplify it. Okay, and then multiply by x pi, integrate over x pi. And the reason that we can simplify it is because we can combine these two differential operator and write it like this is J dot into this gradient pi of N dot X pi in the X pi direction, EQ X pi. All right, so this two terms combined to this term because there's something like a distribution rule. So you're taking the gradient pi of this multiplication of this times that, you basically operate on. So gradient pi of this one, which is give you this term multiplied by x pi, which is this one. So this term, or this one multiplied by gradient pi of this one. So you can using the distribution rule. So adding this term would be with this term. Okay. Now, then that will allow us to do a different integration by part, because again, we can rewrite this one as a divergent point of J times this vector in dot x pi in x pi direction. Okay, but then minus the divergence of j of this one. Divergence pi of j and multiply by this vector in dot x pi integration x pi. So basically divergence of this vector will give you this one plus this one. So you can write this vector as the divergence of this, subtract this one. Okay, that's basically what we do integration by parts. Now the first term is a total divergence, and you're doing the volume integration, assuming you are taking a volume that is infinitely large. So this divergence term, we're using the divergence theorem, will give you a surface term right at infinity. And at infinity, J will go to zero because we assume J, the current density is localized near the origin. So when you go to a large distance, this will fall off fast enough, then the whole thing is zero. Okay, so what is left is this. There's only the second term after you do the integration by part of the first term. Now we identify this divergence J as related to the charge density because again, we have the continuity equation, partial rho partial t plus divergence J is zero, and partial t is just minus I omega. So minus I omega is, due to the single frequency mode, so divergence J will be equals I omega rho. We've seen that before. We did the same trick before using for the electric dipole term. Now we do the same thing. So divergence rho, substitute it as I omega rho here. Okay. So, so that will give you only the second term I is I minus I omega over 2. And you have this term is rho times x pi and then n dot x pi dq x pi. All right, so we're almost out of time, but now you're getting something very similar to what we have done in the electrostatic. This one, you see that it will be getting very close to the form of the electric quadrupole. Okay, but before we can do that, we test a little bit of derivation to do it first. Basically, we need to calculate the field first. So after we calculate the field, we'll see that it's actually given by the electric quadrupole tensor, especially the magnetic field. Okay, but we're getting close to that one. All right, but that we need to do more, so we'll wait until Friday to finish that. Okay, and it's kind of hard to see is related to the electric quadrupole, but you kind of see that about the same order because now you have the integration is over all space, and the integram has the electric, it has a charge density, and then you have 2x here. You have x pi here, the x pi here. So a charge density multiplied by the order of x pi square and integrating over all space will give you of the order of a quadrupole term. Although it's not exactly the electric quadrupole tensor that we saw last time, but we'll see that how we relate to that after we calculate the field. Okay, so this is just the integral that we will put in the formula for the calculating the magnetic potential, but after a few more steps, we'll get the electric quadrupole tensor out. Okay, but up to here, any question? before we move on? Anyone? So it's okay right up to here. So the next step will be put this integral into A. So now A will be just going to the formula, the same formula that we have been using. So you have a mu zero ck squared. There's a 4 pi r, but there's a factor of 2 here. So you multiply by 8 pi. I guess some of this omega actually all these change to ck, so you get ck. Now, suppose this minus I also cancel with another I term. So, but anyway, so this should be the correct expression. And now the integration is over this one. So you have x pi n dot x pi charge density equal x pi. Okay, so this is this one. And the rest is combining the rest of the coefficient and get this one. Okay, so this is the equation you to calculate A. So that's kind of simple enough. Now the next step is to calculate H. So H is just take the curl of A, which gives you B, and divided by mu zero. So cancel with this mu zero, then you get H. All right. And now remember that in the far zoom that we only consider in the far zoom or the radiation zoom. Now we take the curl of A, you only take the derivative over the exponential factor, this e to the ikr. And the rest of the dependence like r in here, and then the r dependence in n, we all ignore those because all those will give you a 1 over r squared. I mean, it give you extra 1 over r factor, which is much smaller than taking the derivative of the exponential function because we are in the far zone, r is large. Okay, so what we'll get is taking this one, and so because the technical curve becomes a gradient of this one cos into this one, and gradient of this one give you I, K, N cos into this one. Okay, so H will be, now just copy everything, divided by mu zero, cancel with this, so you have minus I. Now you have a K, add up maybe K cubed. You still have the exponential factor, IR. Now you N cos into that one, right? I mean, suppose the N cos into the integram, but what we'll now do is to put this N actually inside the integram. So that doesn't matter because N doesn't depend on X pi, so you can put that in the integram, okay? And then cos into this one. But then now we'll just rewrite this a little bit. So we write it as X pi, which is this one, and then write it like X pi dot N. So X pi times X pi dot N, which is just a dot product, but if we put it this way, it looks like you can interpret that as you're putting two vector together and dot into N, and putting two vector together has the effect of making it a tensor, okay? And then multiply by rho, and integrating over all space. But the next step is doing something that actually doesn't affect the integral, but we add that to make the form of the electroquadrupole tensor. So we'll minus r cubed, r square, not r square, times n. Actually, the factor is you need the 3 of these. So actually, you divide it by 3, and multiply by 3. So that doesn't change this term, but then you subtract this term. And the reason we can substitute that because n cos n is 0. So you just add a 0 term here. So that doesn't matter. And multiply by rho dqx prime. Okay, so now we get a form that we becomes familiar. So because we define the electric quadrupole tensor in when we calculate the electrostatic field also. So that one is basically exactly this one, but if you remember it as using index form, the electric quadrupole tensor is something like this. So integrating, so 3x of x beta minus r squared delta alpha beta multiplied by rho dqx. Okay, so that what we defined electric quadrupole tensor in the electrostatic chapter. Okay, you still remember that? Well, all right, so now we get this tensor in here. In the vector form is here, is in the index form is here, is exactly the same. Okay. I should say that this is not exact, the bracket is not exactly the tensor is this part, so you need to put the dot n out first, then you'll get exactly the same. Okay, so that, all right. So what we can formally write is like that now. So, right, this integral is a vector that we'll call, this integral, n cos into this integral is a vector we call as a capital Q minus I C K Q over combine 3 and 8, you get 24 pi r your exponential function I K R, and then n cos into Q vector. Now the notation, you need to be a little careful. This is a Q vector is not exactly the same as this electric quadrupole tensor. So what we'll define is this Q vector is defined as so basically Q alpha is defined as this Q alpha beta tensor. Oopsie. Oh, too much. I don't know whether you can see that. And then n dot in the n beta. When you pull the n out of this dot product, so this is part of this one, and then r squared times. This is not a dot product, but you can always insert a identity matrix, or I can rewrite like this.
Could you scroll that up a little bit?
Yeah, I understand that. Maybe.
Can't quite see the bottom.
Yeah. See, now you can see that. Yeah.
That's better.
Now you can see that. Okay. So you have I insert the identity matrix, which is this conical delta, and dot into n. Then you can pull the dot n out. All right. So this is the quadrupole tensor dot into n, and that gives you a vector, what we call Q here. Okay. So, all right. So that is the form of H. Okay. Now this form of the magnetic field, we have actually seen something similar before, because when we consider the electric dipole term, actually we have something similar, but with n cos p. The p is the dipole electric dipole moment. Okay, and Oh, the coefficient is different, but then the vector structure is the same. It's n cos in the vector. Now you also get n cos in the vector, but this vector is a q. This q is given by the quadrupole tensor dot into n, but otherwise the same, n cos into a constant, I mean, not a constant in the sense of after you integrate all the expand, but there's n dependence in q also. But it's n cos into a vector. Okay, so h. Once you have h, you can calculate E, and we have done that before because in electric quadrupole, if n cos p and the electric field proportional n cos p. Okay, so we could do that. And now once we have electric field, we can calculate the Poynting vector, and then the radiation power per solid angle, what we call the differential power. And then the differential power proportional to n cos q's absolute value squared. Okay, and when we get the coefficient right, then it will be the correct expression. So now we'll skip the part of the electric field, but just write down this differential power, which follow exactly the same procedure of the electric dipole term. So we have this c squared, and then this z0 factor that Jackson always used. And then you have k to the 6th power. So all this is coming from all the coefficients. If you get those coefficients correctly, then you get that, and then you have n cos q absolute value squared. Okay, so that is the differential power. Okay, the difference, one major difference is that it proposes the k to the 6th power. If you look back on the electric dipole term, this is actually just k to the 4th power. In that case, it's n cos p cos n absolute value squared. Okay, and then the coefficient, of course, is also different, other coefficient, but it's, if you keep track of everything correctly, you will get this result. Okay, so it's not very different from before, but what we get this. Now, when we calculate total power, there will be a difference because Q actually depends on N. There's a dependency of N also in Q because Q is the Q vector is the Q tensor dot N. There's extra N here. Okay, so when we integrate over all solid angle to get the total power, then you take into account of the N in Q also. All right, so that makes it a little bit more complicated, but we'll go through that quickly to see if you have any, if you actually can get some idea that how you actually integrate this kind of thing. It's not difficult, but it's just a little tedious. But we'll, if you just go through it carefully and follow everything, do everything correctly, then it should work out. All right. So, but before we do that, any question about getting to this formula? It's okay for everyone. So
I just have a quick question. What is k to the power of b again?
not B, 6.
6. Okay.
The 6th power.
That makes sense.
This is the 6th, number 6. Yeah. Because if you remember that the previous expression, we have k to the 3rd power. Let me show you how we got this. All right, the final formula that we have, H has C to the k cube power here. And you calculate electric field, which is just proportional to the curl H. You also get an extra k to the third power, then you get the Poynting vector. So combine the two, you get the k to the sixth power. And this corresponding power in the electric dipole term, there's a k square here, and the electric field has a k square. So the total, the power, the differential power, and the total power also proportional to k to the fourth power. Okay, so there's extra k square factor in this in the electric quadrupole term, and that make it a lower order term now because k is inversely proportional to wavelength, and wavelength is in our assumption is a long wavelength, so that assumed to be large. Okay, so k, an extra k square will make this the power smaller. Okay, at least when you consider order of magnitude, this is an order of magnitude smaller. I mean, in the power expansion, that is a higher order term than the electric dipole term. Okay, so that's the major difference in this formula. All right. Another difference is the extra n dependency in Q. So when you get the total power, that we need to be a little careful. So we'll do that now. So, and the first step will be very similar to what we have done for the electric dipole term. So this absolute value square, you just write like this dot into the complex conjugate of this. And after you combine all the terms, you see that it becomes a q square minus n dot q square. All right, it takes a few steps to do that because this is a triple product. So you can write it like two terms. So you have a q term with n dot n, and then you have n vector dot multiplied by n dot q. Okay, and then you multiply this with its complex conjugate, so you get 4 terms, and 3 of the terms you combine to this term. Okay, so basically is how you get this. All right. Now we can use the expression that Q is proportional to, I mean, it's given by the quadrupole tensor dot into n. So you can write it like in the index notation. So like the first term Q square is Q alpha beta. Okay, and multiplied by Q, multiplied by n, like n alpha. No, not n alpha, because n beta you dot into the tensor. So you have tensor dot into n, so you dot into n of n beta, but then you have multiplied by its complex conjugate. So, and they take the dot product, so you get the same alpha, like using gamma. And take a complex conjugate, either one, take the complex conjugate is fine. Okay, and then n gamma. Okay, and sum over alpha, of course, when you have repeated indices, it means that you sum over alpha from 1 to 3. Okay, so that's the first term. Okay, now the second term is this idea is a dot product. So you have 2 dot products. So you have minus. So the first one is n alpha q alpha beta n beta. Okay. And the second one is exactly the same, and gamma q gamma delta complex conjugate n delta. Okay, so basically it's each one of them is n dot q. And then you have 2 of them. This one multiplied by its complex conjugate, so you give them this one. So now you have 2 terms. The first term proportional to 2n. You have n beta, n gamma. So you multiply these 2 together. And the second term have 4n. 1, 2, 3, 4. Okay. And now when you do the total power, you need to integrate over all solid angle. So there's you need to integrate all this n with respect to the angular or the angular dependency. And remember, n is just the radial unit vector. So n, for the radial unit vector, you have a sine theta, cosine phi, express it in Cartesian coordinate so that you get all the angular dependency out, and that help you do the integration. That cosine theta, z. Okay, so that is just the unit vector along the radial direction. Okay, so now you have this one. You can put all the component into here, all these terms, right? So all these are in index notation, basically saying that n1 is this. So n sub 1 is sine theta cosine phi, n sub 2 is sine theta sine phi, n sub 3 is cosine theta. Okay, and you substitute into all these, and all right, is it too complicated for all you? Is it? Can you follow all these? All those tensor notation? Is that too hard to keep track on?
Yeah.
Yeah, so it's hard. Yeah, sometimes when you work with tensor, you just need to be a little patient and just keep track of everything and don't get scared of the complicated notation or complicated expression. It's nothing but just indices of this vector or this component of the vector. Okay, so you have alpha, beta, gamma, delta. Each one goes through 1 through 3. Okay, and 1 to 3 is just the XYZ component. So this is the first component, second component, third component. We just need to substitute all these into all these expression, integrate over the solid angle. Okay, it looks difficult, but we'll see we can get some pattern to solve all this integral. And you see that this is actually not that hard. So remember this solid angle integration, right? The solid angle d omega is just sine theta d phi. And integrating over solid angle means you integrate theta from 0 to pi and integrate phi from 0 to 2 pi. Okay, so that's what we'll do. Okay, and now the first expression is this x, this square term, your 2n. So beta and gamma, you can have all the combination. But the first thing you notice that based on all these components, if you have the product that have different indices, say n1, n2, or n1, n3, okay, and when you integrate that, that will be 0 because there's a cosine here, there's sine here. So if you multiply this with that, then you have sine phi, cosine phi, integrate over 2 pi, 0 to 2 pi, that will give you 0, okay? Because that's just the multiply together is a total, still a sinusoidal function. And if it's still a sinusoidal function over 0 to 2 pi, you integrate 0 to 2 pi, will get exactly 0 because you get the same up and down. So, and the only thing that will make it non-zero is either doesn't depend on phi, like square of the 3 components. You have n3 square, just cosine square theta. You integrate over 0 to 2 pi, you just only get 2 pi for the phi integration. Or the n1 square, you get cosine square phi. Then the phi integration will give you just pi. Okay, and likewise, sine square will give you sine integrate over phi will give you pi also. Okay, so Does it make sense? So can you follow me? So
Yeah,
basically this
see
input,
where that's coming from now. Yeah,
yeah.
that was a little tricky, but yep.
Okay, so what I'm saying is this n, if you consider this quadratic term, you have n alpha, n beta integrating over all solid angle, that will equals to 0 if alpha not equals to beta. Okay, so that's the property. You can see that, right?
Mm-hmm.
Okay, so so once we have that, then at least for the quadratic term, is simplify a lot because now you can just consider 3 possibilities. So n3 square or n. Let me just write n3 square. The omega just becomes cosine square, right? Just now it's just integrate over cosine square d omega. Okay, and this one for the phi term, you get 2 pi from this one. Sine theta d theta, you can change it to minus d cosine theta. And the minus sign you can use to flip the upper and lower limit. And the result is like we worked that before, worked that out before. Okay, then you get 4 pi over 3. All right. And now the nx squared and ny squared. You see that it actually exactly the same, although the reason may not be the same. So like n1 squared. Now this is n1 squared would be sine squared theta. And then you have cosine squared phi. And then d omega. Okay. The omega will be this one, sine theta d theta d phi. And the phi integration will give you just pi instead of 2 pi because you have cosine squared, right? That you can use a trigonometric identity and change it to sine, cosine 2 phi, and then you see that how you get to 1/2 of the integration from 0 to 2 pi, then just give you pi. Now sine squared theta multiplied by this sine theta d theta, that can also be integrated because sine squared theta, using the same trick, this becomes 1 minus cosine squared theta. And we already know how to integrate cosine square. You get this one. And 1 is also easy because it's integrate from cosine theta is -1 to 1. Then you get 2. Okay, so so altogether you will see that this also gives you 4 pi over 3. Okay, and likewise n2 square will give you exactly the same. So because this one it will give you just sine squared phi instead of cosine squared phi, but the integrating over phi is still exactly the same. Okay, so end up so combining all these, you get the final result is n alpha n beta. The omega is just 4 pi over 3 conjugate delta alpha beta. Okay, so that is the final result for the first term. So you know how to integrate the first term. All right. So because finally when we need to get the total integration radiation power, integrate this one with respect to all solid angle. For the first one, you know how to do it because when you integrate over solid angle, you get just this one. Okay, so that's this one, the first term. The second term has 4n, so now that is getting more and more complicated. But the similar trick actually apply. Similar trick will apply. So you have 4n, and many of those terms will get exactly 0 because of this integrating over phi. the only combination of integration that would not be zero is you have square of cosine phi or square of sine phi, or multiply it together. So cosine square phi, sine square phi, or cosine 4 phi, sine 4 phi, or you have constant term. Okay, so only those terms will be non-zero. And I'm running out of space. See if I can. Let me try to see. Or writing it out a little bit, saving some space. So the first easier term is this sine. Actually, I use n3 square. Actually, not square now. Now you have 4 of them. N3, 4 d omega. Okay, n3 is just cosine theta, so it's cosine 4 of theta. And the integration will be very similar to this n, this one, except that now you have cosine 4. So, and you know how to do that because combining this, you get d cosine theta, this power of cosine theta. So that will give you a little different from before. Instead of 4 pi over 3, actually get 4 pi over 5. Okay, so that's n3 fourth power. And other non-zero term will be like nc squared will be cosine squared theta and multiplied by so either n1 square or n2 square. Okay, so and one trick is that instead of integrating up those separately, you can like nc squared times n squared d omega. Okay, but n squared is always 1. N squared is just n1 square. Actually, for consistency, it's n3 squared. N squared is just n1 squared plus n2 squared plus n3 squared, but it's combined to 1. So this is exactly what we had before. So this is 4 pi over 5. Okay. And then, and if you do it the other way, so you have separated together. So you have n1 squared plus n2 squared plus n3 squared, but we already done the n3 squared times n3 squared will give you this one. So what is then the other two terms, you have n1 squared and n2 squared, but by symmetry, you know that they actually give you exactly the same contribution. So n1 integrating over n1 squared and n3 squared is the same as n2 squared and n1 squared. So you can write it like, this is 3. This is 3. 3. So this is n pi over 5. 2 of these n3 squared and 1 squared d omega. And likewise, this after you get that n3 squared and n2 squared is exactly the same. So what we have is n3 squared and 1 squared equals to n3 squared n2 squared integrate over a third angle. So that is just this minus that divided by 2. That will give you n 4 pi over 15. Okay, so now what is left is the n1 squared, n2 squared, n1 squared, n2 squared. That have sine 4 theta, cosine square phi, sine square phi, d omega. All right, and that, I mean, looks complicated, but if you solve it separately, so do the phi integration and then theta integration. Theta integration is just the same as before. So change sine 4 theta to 1 minus cosine square theta square, the total factor square, and then integrating over d cosine theta, so that you know how to treat this. And this one is you just keep using trigonometric identity, and you can solve that. Or if you want to save some trouble, put it in a computer, you'll get the exactly the same. So that will give you actually exactly the same formula. All right, so you work out everything, you get this vector. Okay, and finally we'll have this n 1/4 power. And you see that this actually should be exactly the same as n2/4 factor. And this one is still exactly the same as this one, except that now it's sine 4 theta cosine 4 phi. Right? And you can work out all the details. And you get exactly like the n3 to the 4 power 4 pi over 5. Okay, so this one equals this one actually equals to this one equals to 4 pi over 5. All right. Now we work out everything. The rest, all the other terms, all the other combination will be exactly 0 due to the phi integration. So altogether, this integration n over n beta n gamma n delta d omega. You combine everything, you get 4 pi over 15 times delta alpha beta plus, not this factor, delta gamma delta plus delta alpha gamma delta beta delta plus delta alpha delta beta gamma. Okay, if you combine all this result, you get this because say if all of them the same, you have this one the same. This is 1, this is 1, this is 1. So altogether it's 3. So and then 3 divided by 15 is 1/5. So we cover all this. But if instead just 2 of them the same, so you have one factor is 1, the other 2 factor is 0. So you get 4 pi over 15, just like before. Okay. But if it's not these 2 cases, then all 3 will be 0. All these will be 0. Okay. Then you get 0. All right. So that is, once you have that, you know how to integrate the second term because that's the only proportion of this n over times n beta times n gamma times n delta. And you can integrate it out. Okay. So, okay. Any question up to all these mathematic consideration? At least the method, can you follow all the method and the reason why we can get to the final much simplified result? Any questions? So finally, we have this result and this result so that we can use. I mean, you might not be able to follow all the details because some of these you might need to work out a little bit. But finally, this is what we get. Is that okay for everyone? So,
Yeah, it explains the book. If
Yeah.
you're following the book, I'm following along, and that's
yeah.
that's better.
Okay. So yeah, it just takes some tedious work, but I mean, if you're patient enough, then you should be able to get that. But we spend some time in doing that because the final result is quite straightforward and quite simple. So we want to spend some time to get at least mathematically why this is so. Okay. All right. And now remember that integrating over this factor has 2 terms. One is a proportional q squared, the other is q dot n squared, minus the other one minus q dot n squared. And when you put it in index notation, then that depends on all those n power. You integrate over solid angle, you can use the two result that we had and use all the conical delta. And finally, you will get this result. Actually, I should write it on the next line. Equals to 4 pi. And the first term is q squared. Each q is proportional to the tensor q dot n. And then you have to do all this n squared. And then you get conical delta out. So what you mean is the conical delta will give you q alpha complex conjugate q alpha beta. So it basically sum over all beta. They have to be the same because the 2n has to be of the same. So previously this is not the same because one is this tensor dot n, the other is the other tensor dot n. Then the dot n, the n index may not be the same, but after you get the conical delta, they must be the same. So you sum over the second index also. The first index you sum over because you are q dot q vector dot q vector. So you already sum over this one. So finally you get that, and the coefficient is there's a 1/3 coefficient based on the integrating over a solid angle. Actually 4 pi over 3, but you pull over 4 pi because the other one also proportional to 4 pi. So the other one is you have a 1/15. Now you have two terms in that. After you sum over all the conical delta, one term is proportional to the trace of the quadrupole tensor multiplied by its complex conjugate. Okay, and then you have this 2 alpha beta complex conjugate q alpha beta. Okay, this is just coming from summing of all the conical delta because you remember that integrating over the fourth power n, the final result has 3 terms. Each term has the product of 2 conical delta, and you work out all the conical delta, you get this one out. Now the main idea is that this Q tensor is defined as traceless, meaning the trace is sum over all the diagonal term. So it's Q11 plus Q22 plus Q33. This is exactly 0. This is by design, they're 0. Because remember when we define the Q tensor, we add the extra n term. The extra n term is just to make sure this is traceless. This is exactly 0. Okay, and so now we end up with just this factor, and you see that this factor, exactly this factor, except that the different coefficient, but we can combine all the coefficient and get just this one. And this one is sum over all the repeated indices. So you sum over alpha, sum over beta, sum over alpha from 1 to 3, sum over beta from 1 to 3. But otherwise, they are exactly the same. And one is the complex conjugate of the other. So finally, you get the total power after integrating over solid angle and getting all the coefficient correctly. So the coefficient, just you need to be careful about this, all these coefficients. And then finally, it's proportional sum of alpha, sum over beta from 1 to 3, and all the components of the electroquadrupole tensor. Okay, so that's the final result. All right, so the total power is kind of a little bit simple in the sense that it's basically just the electric quadrupole tensor, but all the component, you take the absolute value square of the component and then sum over all 9 of them. Okay, that will you get this factor and multiply by this coefficient, you get the total power. Okay, so so the process to get to the final point is kind of tedious, but then the final form is actually quite simple. All you need to do is once you calculate this electric quadrupole tensor, you just sum over the absolute value square of each component, each of the 9 components of the quadrupole tensor. You get this factor, and then the rest is just multiplied by this coefficient. Okay, so it's not too bad after all. Okay, so at least you get the process how you get this formula. It's okay for everyone, and anyone need more explanation for how we get to this point? Is that okay? All right, so this is the final formula that you can use. Okay, so now the total power is the process of calculating the total power is just like the process of calculating the electric quadrupole tensor. Once you have that, you can use this formula to get the total power. Okay. All right, so we now treat a special situation that will give you more geometrical understanding of the differential radiation power. Just like the electric dipole power, we remember that you have this sine square theta distribution, right? So you remember that correctly. So, but there's something similar for the electric quadrupole term also, but we need to assume a little bit of the form. So because that will simplify the calculated angular dependence of d omega d phi. So remember d omega d phi is proportional to this one, n cos q dot cos n, right? So we want to simplify that using a special geometry. Now we can consider this q alpha beta using a special geometry that it's traceless. So we can assume that the 3 component is just a constant Q0, and then the other 2 is just identical to minus Q0 over 2 minus Q0 over 2. So both Q11 and Q22 are this one. So you add up Q11 plus Q22 plus Q33 is 0, and the rest are 0. Okay, so we consider this Q alpha beta is for this special case. We can write like that. There's not all quadrupole tensor can be written this way, but now we're just saying that we can. Somehow we can do that for a special case. All right. Now once we have this Q tensor, we can calculate the Q vector. Q vector is just Q tensor dot n, but for this form, so you can write out explicitly. So you have Q0 over 2. So dot into n. So n1 is sine theta cosine phi, but you multiply by minus Q0 over 2, so you have this one. N2 is sine theta sine phi. So that is this one, and Q3 is cosine theta, so you have 2 cosine theta. So that's the Q vector. Okay. And now remember this vector is equals to Q square minus n dot Q square. Okay. And Q square for this one, so Q square assuming Q0 is will, then the total expression actually is will. So you have Q0 over 2 square, and then square of this plus square of this plus the square of that. So you have Q0 over 2 square. So you have sine square theta. Square of this plus square of that, you just get your sine square theta. All right, and the second term will be a 4 of cosine square theta. Okay, so that's q square, and then n dot q square. Q square. All right, so n dot q is, so basically this one dot into n. So this one dot into n. So n1 is just the same. So you have basically minus n1 square, and then minus n2 square, and then this one dot into n is just 2 cosine square theta. Okay, so that will give you q squared over 2. Everything will be square. So you have this one square of this, like this one times, yeah, minus square of that. So you have minus sine square theta, and then plus 2 cosine square theta, and then everything squared. Okay, so now you have the final result is this one minus this one minus this one. Okay, so now I mean the rest is just a little bit tedious formula, but and then you have this square of sine theta, you have sine square theta. Okay, and then minus 2 of these and this, so minus 4 of sine square theta cosine square theta. Okay, I'm just wondering, do I get all the simplification that we want? I mean, I probably, I mean, I worked out that in my notes before. I mean, the rest is just basically simplifying everything. So this is already square over this one. So you want to combine everything. This is a 4. Combine everything, and you see that finally you see that they have some cancellation, and the only thing left is what is left is 9 sine square theta cosine square theta. All right, so it might take a while to simplify all this, but the final result is this: you only have this sine square theta cosine square theta. All right, so that is proportional to the dp d omega. Remember, dp d omega is proportional. This absolute value square now is proportional to sine square theta cosine square theta. Unlike the dipole term only proportional to sine square theta, now is have extra cosine square theta. So you again plot in the polar coordinate. So this is z direction. So dp d omega will be 0 along 0, theta equals 0 and theta equal pi because of these sine square terms. But it also will be 0 along all the perpendicular direction, the x direction or y direction, or all the transverse direction perpendicular to z direction because of this cosine square term, because cosine pi over 2 is 0 and theta is pi over 2. So, so not only 0 along the z-axis, but all the other axes also. So the power will be something like this. So it's all of these. I mean, they're exactly the same, but there was just copy from one to the other. So the power will be 0 on both the parallel and exactly perpendicular direction. So somewhere maximum in this, the direction in between of some finite theta in between 0 and pi over 2. Okay. And likewise, symmetric with respect to C, positive and negative C, and then of course there's a rotational symmetry, so you get to rotate, it's exactly the same. So it depends only on theta, not phi. Okay, so that is the kind of the distribution, power distribution of this quadrupole radiation power. So dPd omega is proportional to something of this shape. Okay, so again, if this is theta, this length is proportional to sine square theta cosine square theta. So that's this length. So we'll have the shape like that. Okay, so that's the dPd omega for electric quadrupole. Then that should be the rest of this 9.3 section. All right, but any question before we go? We are out of time now.